Welcome to the Explainer. Today, we're going to decode a pattern of movement that you see literally everywhere, a secret rhythm that pretty much runs the universe. We're talking about everything from the jiggle of atoms to the swing with a grandfather clock. So let's jump right in.
So let's just start with this question right here. A swinging pendulum, a guitar string, atoms. I mean, what could they possibly have in common, right? They seem like they're from completely different worlds. But believe it or not, they are all dancing to the exact same hidden beat. And today, we're going to figure out what that is.
All right, to really get a grip on this special rhythm, we've got to start with the basics. We're going to look at all the different ways things can move in a repeating pattern. Think of it like we're starting with a big, wide-angle lens, and we're going to slowly zoom in to find what makes simple harmonic motion so special. Okay, first up, periodic motion. This is like the giant umbrella category for any movement that just repeats itself over and over again after the same amount of time. Think about the Earth going around the sun. It takes a year every single time. Or the second hand on your watch goes around in 60 seconds, like clockwork. The key here is just that it repeats on a regular schedule. The actual path it takes doesn't really matter for this definition. All right, let's zoom in a little. Now we're talking about oscillatory motion. This is a special kind of periodic motion. It's not just repeating, it's specifically a back and forth or a to and fro movement around a fixed central point. We call that the equilibrium position. So picture a kid on a swing or a guitar string after you pluck it. That's oscillation. Okay, so here's a key idea. All simple harmonic motion is a type of oscillation, but not every oscillation gets to be called simple harmonic motion. So what's the secret sauce? What's that one special rule that makes this dance the universe's absolute favorite? You know, you'd think something so fundamental would be super complicated, but it's not. It all boils down to just one single elegant rule. That's it. This is the secret recipe we've been looking for. And there it is. F is proportional to negative x. So what on earth does that mean? It's actually pretty simple. The F is the force pulling the object back to the middle. The x is how far you've moved it away from the middle. So this rule says the farther you pull it, the stronger the force pulls it back. And that little minus sign, that's the real star of the show. It just means the force is always pulling in the opposite direction of where you moved it. It's constantly trying to get back to the center. This right here, this is the soul of simple harmonic motion. And that force has a name, the restoring force. The name says it all, right? It's always trying to restore the object to its resting spot. The best way to think about it is like an invisible rubber band. The more you stretch that rubber band away from its relaxed state, the harder it snaps back. That restoring force is the engine that keeps this whole back and forth dance going. Okay, so we've got the main rule down. Now, let's learn the language. To really talk about this motion, we need a few key terms. Think of it as learning the anatomy of this wave. So check this out. If you were to plot the position of, say, that bouncing spring over time, you get this beautiful, smooth, repeating wave. It's not just any old squiggle. This specific shape is a sine wave. And that sine wave is the visual signature. It's the fingerprint of simple harmonic motion. First term up, amplitude. Super simple. You see how high the peaks of that wave are? That's the amplitude. In the real world, it's just how far the object gets from its center resting point. So for a swing, it's how high you go. For a spring, it's how far you stretch it. It's basically the size or the intensity of the oscillation. Next, we've got the period. That's just the time it takes to do one full cycle. One complete back and forth. On the graph, you can measure it from one peak to the very next peak. It's simply the time for one full repetition. And that brings us to frequency. Frequency is kind of the flip side of the period. Instead of asking, how long does one cycle take, frequency asks, how many cycles can you fit into 1 second? It's measured in hertz. So they're opposites, right? If something has a long period, it's slow, so its frequency is low. If it has a short period, it's happening really fast, so its frequency is high. All right, we've got the look and the language down, but now let's get into the inner workings. What's going on with the object's speed and its acceleration as it moves? And I gotta tell you, this part is one of the coolest, most mind-bending parts of the whole topic. Just look at this table. It's totally wild. Right in the middle, at the equilibrium point, the object is moving its absolute fastest, but its acceleration is 0. And then at the very ends, the extremes, where it stops for a split second, its velocity is 0, but its acceleration is maxed out. How does that even work? It sounds completely backwards. Let's go back to the kid on the swing. Picture it. When you're at the very top of your swing, right at that peak, You hang in the air for just a tiny fraction of a second, right? You've stopped. Your velocity is 0. But in that exact moment, gravity is pulling you back down with everything it's got. That pull is the force, which means your acceleration is at its absolute maximum, ready to yank you back the other way.
Okay, now what happens at the very bottom of the swing? You're flying, right? You're moving at your fastest possible speed. But for that one instant when you're perfectly at the bottom, the restoring force, the force pulling you back to the center, is momentarily 0. And if force equals mass times acceleration, and the force is 0, well, then acceleration has to be 0 too, even though you're moving like a rocket.
So we've got the motion, the rules, the speed. But what's fueling all this? What's the power source? Well, it's all about energy. The whole show is just a beautiful, continuous trade-off between two different types of energy. So here are the two players in our energy game. First, you have potential energy. That's stored energy. Think of it as the energy of position. When you stretch a spring, you're loading it with potential energy. So it's at its max at the ends. Then you have kinetic energy. That's the energy of motion. It's highest when the object is moving fastest, which we now know is right in the middle. And they're in this constant dance. When one is high, the other is low.
And if you look at these graphs, you can see it plain as day. The potential energy curve is a U shape, lowest in the middle and highest at the ends. The kinetic energy curve is the exact opposite, an upside-down U, highest in the middle. They are perfect mirror images of each other. As one goes up, the other comes down by the exact same amount.
But here's the most beautiful part. Even though these two energies are constantly changing and trading places, if you add them together at any point in the cycle, you get the same number every single time. The total energy, as you can see from that flat line on the graph, stays perfectly constant. No energy is created or destroyed, it just gets passed back and forth between potential and kinetic. It's a perfect closed system.
Okay, we've gone deep into the rules, the definitions, the energy, but now for the big question. So what? Why should we care? Why does this one particular pattern of movement matter so much, not just in a physics class, but in the real world? Because this simple motion, it's literally everywhere you look. It's how a grandfather clock keeps perfect time. It's how a sitar string vibrates to make beautiful music. But it goes so much deeper than that. It's the basic blueprint for understanding all waves, sound waves, light waves, you name it. It's even how we think about the vibrations of molecules, which is what we feel as heat. It is the fundamental rhythm of the universe.
So that kind of leaves us with one last big idea to chew on. We call it simple harmonic motion. But the fact that this one pattern shows up everywhere, from a bouncing spring in your hand to the behavior of light from a distant star, well, it suggests something pretty profound. It suggests that maybe the fundamental rules of our universe aren't chaotic or complicated, but are instead based on an incredibly elegant, simple, and rhythmic foundation. A huge, cosmic idea, all hidden away in something as simple as a swing.